Okay, thank you for being here. So my goal here is to explore 4D parallel computing for space-time simulation. So first of all, some observation. Supercomputer becomes bigger and bigger, and there is a lot of resources inside. So for example, in France, we have here in Joliot-Curie, which has almost 300,000 cores. And also, I want to point out that there is a huge amount of memory, more than 500,000 terabytes, and most of the code don't use this memory. So also another observation, in classical time stepping, there is no time parallelization. We do that step by step, and we can adapt the time step, but it's driven by the minimum one in space. So it's a uniform time step in space. When we refine the mesh, you have also most of the time to reduce the time step. And if you want to keep the same workload on each core, we have the simulation time that will double at I would say. And also we have an incomplete result storage and costly disk usage for the simulation, because even if we don't store all the increments, we have a huge amount of data on the hard disk. So the goal of my talk today is to explore this 4D space-time simulation, combine it with anisotropic mesh adaptation to have a kind of adaptation in time and in space. So this is done in ECTech, which is an in-house library. And the goal to develop in this library is to combine optimization. So the first one is anisotropic mesh adaptation to reduce the problem size. The other one is to enable parallel computation to increase the computational power. Also multi-grid solver. Yeah, I didn't tell that, but we do more implicit solver. So we have to solve very large systems sometimes. And for that, we can use multi-grid solver to reduce the algorithm complexity. And we can also plan to use high order element to increase the accuracy. And we want to combine everything, all this optimization to have an efficient solver. So this new one is to explore space-time simulation. So the context, now I will give you some numbers about ND meshes characteristics. I will do some parallel mesh adaptation performance, including 4D, and then I will move to space-time simulation, including a kind of visualization. First application to the advection equation, and I will conclude. So first of all, here, the test case was only a unit cube in any dimension with a mesh size of 0.1. And here you have some information about the number of nodes, the number of elements. Maybe more interesting for us in parallel computing, the number of boundary nodes. The neighboring nodes to a node, the neighboring element, the number of neighboring elements to an element, and also the size on the disk. That could be interesting. What we can notice is that in 4D, there is a huge amount of nodes that are on the boundary, because the 4D is very compact domain, and that could limit the quality of the mesh and also the parallel efficiency that we have developed. And also the ratio between elements and node increased significantly with dimension. That explains why the cost of that is increasing quite a lot. Some other numbers in this unit cube, if we see about entities, so the number of nodes in each mesh, the number of edges, triangle, tetrahedra, and pentatop, or 5D cells, or 4D cells. And we can see that in 4D, even if it's only a mesh size of 0.1 on a unit cube, you start having a huge amount of entities. So 40 times more triangle than nodes and so on, something like that. So if you plan to use high order elements in 4D, it will be quite costly. An image of a pentatop element. So maybe if you have the animation, it will be a little more clear. So here it's a trace on a 3D cut of a 4D element. So it will appear there. And here the time represents the fourth dimension. Yeah, thank you. So just to see that we can have a kind of visualization of that element. So now moving to parallel mesh adaptation, the strategies we have developed from quite a long time is to do local remeshing with frozen interface. Like here, the initial mesh, we just remesh inside the domain and keep the interface unchanged to get a conforming mesh. Then we just move the interface inside the domain like this, for example, here, and we reapply the local remeshing and so on until we have a good quality mesh at the end. So at the end, a final repartitioning step is done to load balance the work for the finite element solver. So this is a 2D test case, but it's working in 2D, 3D, and even 4D now. And here it's some parallel performance we have achieved in 2D and 3D up to 100,000 cores, which is quite good. Here's the CPU time, depending on the number of cores we use for the same workload per core. And this is the kind of mesh we can adapt. So it's unstructured, unhierarchical meshes, anisotropic one, here around the neuron. And we have I will go back on that later, but a phase that a level set that represents the phase. The red part is the inner part. The blue one is outer part of the phase. And we have this kind of 3D anisotropic mesh. So if I move to 4D parallel performance, so here up to 8,000 cores, you can see that there is a decrease of the performance at the beginning, but this is mainly due to the number of neighboring subdomains that increase. For example, on 32 cores, we have 16 neighboring domains, 30 on 500 and 34 on 8,000. And after that, it's quite constant, which is good for scalability, I would say. The drawback for that is that we have to use quite huge domain in 4D. And for doing that, we have to use underpopulate nodes. So we don't use the full power of the supercomputer, but only 1 core over 2. So that's to be a little better in terms of performance. I try to use I implement the first version of hybrid OpenMP MPI version, which is quite poor performance, only 1.5 on 4 cores. The main thing is that it's very limited. So only the measure is multi-threaded, not the repartitioner part. And also the location of the OpenMP loop is very low. And so we don't take advantage of OpenMP at that time. Some good points, there is bigger domains, so less ratio of nodes on two interface nodes, and also less constraint on the measure, so fewer frozen nodes, and so we can have better quality mesh. So the conclusion is that at that time it's not interesting, but I think it's the way to go. Some largest mesh generated in 2D, 3D, and 4D. So 2D, 3D, I use the full-scale Aaron Joliot-Curie supercomputer, and I reach 2,000 billionths elements mesh in 2D and in 3D. In 4D, I use only 16,000 cores, and I reach 5 billion and 100 billionths element in 4D. With quite good quality mesh, a number of neighboring domain that is still reasonable, and of course the CPU time increase. Good point also, we are able to store the results, which are quite huge, and with a high bandwidth between the disk and the memory and the CPUs. Now moving to anisotropic mesh adaptation with around the level set for multi-phase flow or multi-phase representation. So we use a signed distance mainly, so positive inside, negative outside, and we define a parameter epsilon, the thickness, to represent the smooth interface between inner and outer part of the phase. This level set function is used to mix properties, for example, the density or so on, and also to perform some mesh adaptation across this level set that will concentrate the nodes where we need it. This is some 3D test case we have done with that. So here I represent only the iso volume, the positive part of the level set. So one was a 3D flow around the microstructure. So it was more, not Navier-Stokes, more Stokes equation, because it was for composite materials. Here I think there is 10,000 fiber, and we compute the flow around them. And here it was more challenging. It's a 3D mesh of the Earth with a level set that represents the Earthland elevation at Earth level with some details that are close to 100 meters. So here we need quite a huge computational power. Now, space-time simulation. Yeah, it's okay. So the classical advection test case. So it was the most straightforward equation I can do in 4D. So the classical formula becomes only v tilde dot grad tilde alpha equals 0 with an extended velocity, the classical velocity v and 1 in time, and the extended gradient with 0 alpha of 0t on the fourth direction. So we use a classical finite element to solve that, including SPG stabilization. And the Dirichlet boundary conditions that are set on the hyperface t equals 0 will represent the initial condition. The global linear solver system is solved using the PETC library. So this is the results. So first of all, in 1D and time, in 2D and time. And here it's at the end of 20 iterations. So yeah, the test case was just to translate a ball of radius 0.1 with a velocity 0.6 in all space direction. So in 1D, this ball will just, or this segment will just advance in time. The same in 2D, it's a disk that advances in time, and so on. The interesting thing here is that you can see that coupling mesh adaptation, we have some very huge time step far from the interface, inside the domain also, and close to the interface, we have small kind of time step, but it's not time step, because you can see that the elements are stretched or elongated, not in the time direction or in the space direction, but both in time and space. So doing that, we have a quite optimal mesh to do that. So maybe here, the video also, here is to show you the different iteration across the time. So the first, here, maybe if you can make a pause at the first one. So here we start with a coarse mesh, 4D, 3D mesh, but it's 2D and time. And we run the solver, space-time solver, and we obtain this. So it's not good enough, but we still have the way, this that will move there, but with not a good accuracy. And after that, we perform mesh adaptation on that, rerun the solver, and so on, until here I think it's 20 iterations. And at the end, we have a very good accuracy with a quite good mesh adapted to the solution space and time. Yeah, I think you can move after it's not moving so much. So if I do some comparison between the results, so for this test case, we have an analytical solution, so we can compute a L2 norm or L2 error between the computed solution and the analytical one. For 1D, 2D, and 3D space-time simulation, we have a quite good accuracy. Here it's some numbers about the number of nodes and elements used in the final mesh, and of course the CPU time that increased quite a lot with dimension. The time is in serial. Here it's without any parallel computation. So yeah, it's done on the unit cube for this simulation. So in time we have 1 second. So it's a simulation that duration that is 1 second in that case. The L2 error is the same for almost all of them. And doing that, we can, combining mesh adaptation and advection solver in space-time can provide good results. And doing that, we have a kind of automatic, adaptive, and heterogeneous time stepping. But how to visualize this result in 4D? That could be quite challenging. So what we have used right now is we have developed also a mapping solver to map some field between two meshes, because we remesh, so we have to map the original field in the new mesh. And we use these tools to do that. So the input mesh here will be the 4D one used for the computation, and the output mesh will be a 3D cutting plane. And we use classical 3D data visualization to visualize these results. One difficulty, and maybe you have noticed that on the first video I play with the pentatop element, if we use a fixed 3D cutting plane, it must be fine enough to represent the solution, and it will be very fine and very difficult, and we'll lose everything. So the answer to that is to apply again the mesh adaptation strategy on the cutting plane to get quite good results, accurate results on the visualization part. So doing that, if you use some classical view, cutting plane as t equals 0, t equals 0.5, and t equals 1 second, we have the classical time stepping visualization where the initial state in the middle and the last one. But we can also do that cutting plane in x equals 0.5, y equals 0.5, and z equals 0.5. So here the z direction represents the time, and x and y will represent the two other space dimensions. And we have this kind of representation that will be very difficult to obtain in a classical time stepping formulation. Oops. So some wrong, I'm not sure it's so true, but first, let's say comparison between space-time and time-stepping solver. So the space-time was 20 iteration of space-time solver plus mesh adaptation. The final error was this one, and the CPU time was that one. And for time stepping, it was a little, I tried to do something that give almost the same error. It's not exactly the same one, but close to that. 2,500 time step with 80 remeshing step. Here, 3D remeshing step. And you can see that the CPU time is almost the same. So the advantage and disadvantage of that, I would say in time is almost the same. Almost, maybe there is some differences. In terms of memory, of course, space-time uses much more memory than classical time stepping. Here it's 40, here it's only 3D in memory. But we have enough memory on supercomputer nowadays to do that. Another maybe very good or very interesting point is more the storage part. Here you can see that I store only 200 increments on the 2001, and I still have 10 gigabytes of data. And if you compare to the space-time, it's only 300 megabytes. Here, if I want to store all the time step, I will increase that by a factor of 10 or 100, I don't know. And this one will stay the same. So this storage is lossless. You have all the information of the space-time simulation compared to that one. And maybe that's a very interesting point of that. Maybe just to end before concluding, some space-time outspeed up test case from 1 up to 128 cores. So we have quite good performance at the beginning, an efficiency that is quite good. So it's increasing after that, but be careful when parallel efficiency increase. Most of the time it's not so good news. Here it's because the measure cannot do the work correctly. And so the number of nodes in the finite mesh is not converged, and so there is less element, and so it's faster. So just be careful about that. Why there is this problem? Because it's a very coarse mesh, and then there is too much constraint on the solver. So to conclude, we have been able to make some parallel mesh adaptation in 40 up to 16,000 cores with a high quality 4D mesh, 5 billions and 100 billions elements. The scalability is quite good, but we have to use large enough domain to do that. And so we can use underpopulate or the first implementation of multi-threaded version, but it's still with poor performance. 4D space-time simulation have been validated with the advection equation, which is quite straightforward, but show very promising results combining with anisotropic mesh adaptation. And also the global toolchain, including visualization, have been done. And the good perspective is that it's cheap and lose less storage. So future work, of course, try to improve the multi-threading version. We don't want to use underpopulate nodes. And maybe that could lead also to the future utilization of GPUs. Do more complex space-time simulation. Here it's quite straightforward. It's only advection, but equation, multi-phase flow, and so on. Support 4D in more functionalities if needed, for high-order elements, for multi-grid solver or something like that. Many thanks to Glicid and Gency for giving me access to regional and French national supercomputer. And now, thank you for your attention and time to questions. I will just end with this for the question. Thank you very much.